Today, let's talk about an absolutely obsessive months-long mission to create one of the world's most incredible materials right from scratch. It's a story that's packed with dangerous chemicals, some seriously brilliant engineering, and a totally relentless pursuit of perfection. So let me ask you something that kind of sounds like a riddle. How can a solid object, a thing you can hold in your hand, be made of almost entirely empty space? Well, the answer is a material that honestly seems to defy all logic. And that material is called aerogel. It's this synthetic, porous stuff that's so incredibly light. Holding it feels like you're holding, well, nothing. Its structure is this super delicate network of silica that traps air so well that it's one of the best thermal insulators on the entire planet. And it was this bizarre, almost ghost-like substance that totally captured one creator's imagination. But see, the goal wasn't just to make an aerogel. Nope. It was to create a piece that was perfect, aesthetically beautiful, with a clean, well-defined shape and absolutely zero cracks. This personal challenge is what turned a really difficult science project into a full-blown quest. Okay, so step one on this journey is just making the foundational gel. And this part alone is a huge deal. It involves wrestling with some extremely hazardous materials and a problem that honestly seemed to have no normal solution. The recipe, it sounds simple enough. You just mix some methanol, a bit of ammonia, and then the real star of the show, TMOS. This liquid chemical is where you get the silica that eventually forms the whole structure of the aerogel. But as you can imagine, working with it is not simple at all. The danger really comes down to a simple reaction. TMOS reacts with water to create solid silica. Now, what's really fascinating and frankly terrifying is that it can do this inside your body. The creator noted that if this stuff gets in your eyes, it can actually form solid particles under the surface, which could lead to permanent blindness. I mean, the stakes were just incredibly high right from the get-go. So after mixing the chemicals, you're on the clock. You've got less than 15 minutes before that liquid turns into a solid gel. But here's the next massive challenge. This gel is so unbelievably fragile that it sticks to any mold you pour it into. You can't use silicone, you can't use a hard mold. So how in the world do you shape something you can barely even touch? And the solution that was dreamed up for this is it's a perfect example of creative problem solving. It's wonderfully low-tech. You take a cookie cutter, set it on a thin layer of hardened candle wax, and boom, you've got a temporary mold. Once the gel sets, you can just crack the whole thing away from the wax base, and the fragile gel gently slides out, completely undamaged. So clever. All right, so the gel is made. The next logical step would be to just let it dry, right? Wrong. This is actually the most complex, the most difficult part of the entire process, and it requires some pretty fascinating physics to pull off. See, if you just let the gel air dry, this thing called capillary action takes over. As the liquid evaporates, it pulls on the microscopic walls of the gel's pores, and the whole thing just collapses and cracks into a million pieces. The only way to save it is through something called supercritical drying. It's a process that turns the liquid into a gas without it ever evaporating, which totally avoids that destructive surface tension. To pull this off, you need a very specific piece of equipment, a supercritical dryer. And since you can't exactly run down to the store and buy one, our creator had to build a custom high-pressure chamber, one that was strong enough to hold liquid CO2 and heat it way past its critical point. I mean, building this device was a whole project in itself. It took expensive, specialized stainless steel parts that were rated for thousands of PSI. Every single connection had to be meticulously sealed, and a pair of $400 sight windows were installed just to see what was happening inside. The whole thing then went through days of leak testing to make sure it was safe and actually going to work. So, the chamber is built. The gel is ready. It was time for the final, most critical stage. After days of carefully replacing the methanol inside the gel with liquid CO2, the moment of truth finally arrived. But that first attempt would reveal a pretty fatal flaw in the plan. So the process involves slowly heating the chamber up to 31 degrees Celsius. That's the magic number, where CO2 goes supercritical. For the first run, this was all done by hand, with a heat gun just pointed at the side of the metal chamber. It was a ton of work, requiring constant babysitting and tiny adjustments. And the result? Well, it was aerogel, but it was far from perfect. There were major cracks running all the way through the piece. A technical success, maybe, but a total failure in the quest for a beautiful specimen. The uneven heating had created stress and just fractured the delicate structure. It was back to the drawing board. But this failure, this is what led to the key insight. The process itself worked, but the execution was sloppy. The problem wasn't the what, it was the how. It was all about precision. What if the chamber could be heated not just from one side, but perfectly evenly from all sides and with automated temperature control? The new idea was just ingenious. Submerge the entire chamber in a water bath, heated by a sous vide cooker, a device that is literally built for precision cooking. And the contrast between the two attempts is it's night and day. Instead of manual, uneven heating, this new method offered an automated, high-precision, and perfectly even environment. The first result was cracks. The second? Well, that was the big question. And so, after going through the entire multi-day process of preparing a brand new gel, it all came down to this second attempt. After all the research, the danger, the painstaking effort, would this new, more precise method finally deliver that perfect result? After slowly venting the CO2 gas out over an hour and a half, the chamber was opened. And there it was. In the creator's own words of disbelief and triumph, the result was clear. The piece was flawless. The new method worked perfectly. The result was this stunning, translucent aerogel hexagon, completely free of any cracks. The ambitious goal that was set all those months ago had finally, painstakingly, been achieved. And just to put this whole achievement in perspective, this wasn't just a few weeks of work. The project started way back in July. The first gels weren't even made until November, and that final successful run, that wasn't completed until the following March. It was a 9-month journey of trial and error. So what's the ultimate takeaway here? This entire 9-month saga, the dangerous chemicals, the custom engineering, the failures, the brilliant solutions, it was all for this one tiny, almost weightless hexagon. And it kind of leaves us with a final question to think about. What does it really take to pursue perfection?